What's up, mathematicians? In this video, I'll be showing you a couple examples of direct proof. And these are sort of number theory type proofs, pretty straightforward proofs. The first one is the following. It says prove that 1 less than the square of a number, so let's see, 1 less than the square of a number greater than 2 will be composite. In other words, not prime. So let's do it first taking an algebraic approach. So I always like to start a proof by writing out the given and the goal. So our given here is n greater than 2. And I'll add this other thing, and n element of the natural numbers, meaning that it's a counting number, okay? It's 1, well, it's not 1 or 2, but it's 3, 4, 5, 6, etc. So it's a counting number. And so given n greater than 2, our goal is to show that n squared is composite. And by composite, we mean it is not, oops, sorry, made a mistake there. N squared minus 1 is composite. Clearly, n squared would be composite because its factors would be n and n. Okay, so this is a pretty straightforward proof. So first of all, we're going to say, note that n squared minus 1 is equal to n minus 1 times n plus 1. Okay, so this is an algebraic step here where we're factoring n squared minus 1 into these two factors right here that you see. And if you're not convinced of this, you could always FOIL this whole thing out and see that it does in fact give you n squared minus 1. Okay, now we just have to observe, basically, you know, if we look at this, if n is greater than 2, n minus 1 will be greater than or equal to 2. Okay, and so since n minus 1 is the smaller of the two numbers, it follows that this number here, n plus 1, will be, you know, not only greater than or equal to 2, it'll be greater than or equal to 4. N plus 1 is greater than or equal to 4 because we know that n is greater than 2, strictly greater than 2. So we could have said at the top here, n is greater than or equal to 3. It would really mean the same thing because we're only looking at counting numbers. Okay, so what that means is that n squared minus 1 is the product of two numbers, meaning it is composite. So that's pretty much the proof. So therefore, n squared minus 1 is composite. And we know it's composite because it is the product of two numbers, you know, that are not equal to 1. You know, if it was 1 times something, then it could still be prime. But we know that both of these two factors right here, this one right here and this one right here, are 2 or more. And since it has two factors that are 2 or greater, it must be composite. Now, of course, it could have many more factors, right? It could have, you know, dozens of factors. But for it to be composite, we just need to show that it has at least 2 factors. So this is an algebraic approach. Sorry. I would also like to show you a more geometric approach. And so I think this is kind of cool. So we're going to start with the same given. So given And let me just draw a little line here. Maybe I'll do this in a different color just to distinguish. Let's see what colors we got here. Let's go with a purple. All right. So given and the same thing, n is greater than 2. Our goal is to show that n squared minus 1 is composite. Okay, so now instead of doing this algebraically, I want you to consider that, well, we can represent n squared as follows. So represent n squared as, well, let's go ahead and just use the dots on the dot grid paper here. All right, and I'm just going to go ahead and count out 5, but obviously it could be more than 5, it could be fewer than 5, but it has to be at least 3. Okay, so basically we have a square here, right? So this length right here is n, and this length right here is also n, and the area is n squared. That's why we call it a square, right? Definition of basically the geometric definition of a square number. So now what would 1 less than n squared be? So, okay, so then n squared minus 1 could be represented as follows. Okay, so let's do our 5 over, and then we're just going to go 1, 2, 3, 4, and still go over 5 here. 1, 2, 3, 4, and there we go. N squared minus 1 is now the area of this particular, well, it's not a square anymore, but yeah, shape. Now, let's go ahead and draw in lines here and here. Okay. Now, notice that these two are the same, and there's actually, a square inside there. But now imagine you take this region right here, you cut it off, and you attach it up here to the top. Okay, so this is equal to, and let's go ahead and I'll start a little bit lower. So 1, 2, 3, 4, 5. All right, and we'll go 1, 2, 3, 4 across and up the 5. Okay, but now we have this extra part over here. So notice that this right here happens to be n minus 1. And this right here happens to be n plus 1. So this is reminiscent of our algebraic proof from up above. But also notice that since this is a rectangle, this represents, and let me just put it up here, okay. So this represents a composite number. All right, and the reason it represents a composite number is that we can see that along the top is some length, and it is a length 2 or greater, because n is greater than 2. So we have a length along the top, and we have a length along the side. And so the product of those two lengths gives us the total area here, right, of n squared minus 1. So the total area is n squared minus 1, and we see it is the product of two other numbers. And that's sort of a geometric approach, which, I mean, the proof is really the same as the proof up here, but it's done with a more geometric approach, which I think is pretty cool. So yeah, so what do you think of these two proofs? Which one makes more sense to you? And which one do you prefer? So also, as you're thinking about these proofs, as you're watching these proofs, you should be thinking about the prover-skeptic dynamic, right? So I'm acting as the prover and sort of explaining my steps, but you should think about, if you were the skeptic here, are there certain questions that come to mind? Are there things that you feel are not sufficiently explained, or might not logically follow? Are there any logical issues here? I mean, hopefully not. Hopefully not any logical issues, but maybe you feel like there's some lacking in explanation. And so that's the job of the skeptic in a proof, to consider whether this has been sufficiently proven, whether the argument is solid enough to convince even a harsh skeptic that this is in fact true. This conclusion that n squared minus 1 is a composite number, is not prime. Okay, so that was two examples showing, well, one example in two different ways showing direct proof. And yeah, I will show another example shortly here of an indirect proof. So tune in for that. All right, thanks. Bye-bye.